Alrighty, so welcome back everyone. Today we are going to start section 4.2. Well, actually we're going to finish 4.2, I should say, which is going to be covering reduction of order to solve some nice differential equations. But before we get to that, let's knock out the homework from last time. So we're going to start off with number 23, which I wrote backward, colon special. Let's see, we had y double prime minus y prime minus 12y equals 0. And then we are given two potential solutions. We have e to the negative 3x and e to the 4x. Okay? So first thing that we need to do is verify that these are indeed solutions to this differential equation. And then we're going to test to see if they're linearly independent. So first things first, if my y is equal to e to the negative 3x, then y prime is going to be what? It's going to be negative 3e to the negative 3x, and then y double prime is going to be positive 9e to the negative 3x. Okay? So if I now plug these values into my differential equation, I'm going to get 9e to the negative 3x, and then minus the y prime, so it's going to become plus 3e to the negative 3x, and then minus 12 times e to the negative 3x. So 9 plus 3 gives me 12, minus 12 gives me 0. So that one is the solution. Alrighty, now we can test out e to the 4x. So I've got y is equal to e to the 4x. And so y prime is going to equal 4 e to the 4x. And then y double prime is going to be 16 e to the 4x. Okay, now when I plug them in, I'm going to get y double prime, so 16 e to the 4x minus y prime, which is 4 e to the 4x, minus 12 times y, so minus 12 e to the 4x. And so I get 16 minus 4 minus 12, that is 0. So checks out. Alrighty, so if it's okay with you, I'm going to go ahead. You know what? I can probably fit it in. That's a small Wronskian. So to prove that they are linearly independent, I'm going to set the Wronskian. So it's going to be the determinant of my two solutions at the top, so e to the negative 3x and e to the 4x, and then their derivatives on the next row, so negative 3 e to the negative 3x and 4 e to the 4x. Okay, when I do this determinant, I'm going to get 4 e to the x. So I've got 4x plus negative 3x, and then it's going to be minus, but it's minus minus, so this is going to be plus 3 e to the x. And so that's going to give me 7 e to the x, which I can never make 0 no matter what value I put in for x. So therefore they are linearly independent. So that's too close. So linearly independent. Alrighty, so since I know that they're linearly independent, I can now form the general solution. And so the general solution is going to be, this is the general solution, gen sol is going to be y equals some constant c1 times the first solution, e to the negative 3x, plus c2 times the second solution, e to the 4x. And there you have it. That is the general solution, and that is all that we really needed for number 23 after we did the verification. So cool. Hopefully that wasn't too bad. So now we can move on to the next one. Let me clear the screen. Okay, so let's see, we have for 25 the same type of problem that we had in the one previous. So we have y double prime minus 2y prime plus 5y equals 0. And that doesn't look so bad, and then we get the solutions. First solution is going to be that we need to check out is e to the x cosine 2x. And then the second one is, as you can probably guess, e to the x sine 2x. There's usually that symmetry in the solution. So now for the fun part, we need to verify. That's going to be a lot of product rules. So here we go. Let's first off, we're going to say y. We'll do the first one. So y is equal to e to the x cosine 2x. Okay? So y prime is just first times derivative of the second. So it's going to be negative, or you know what? Yeah, I'm doing it all at once. I don't want to do step by step. So negative 2 e to the x sine 2x, like that, right? Plus the first times derivative of the second plus second times derivative of the first, which is just e to the x cosine 2x. Hopefully you'll forgive me for kind of shortcutting that, because now we can do y double prime. So y double prime is going to be, here we go, we're going to have negative 2 times, another product, so first times derivative of the second, which is going to be 2e to the x cosine, there's cosine there, cosine 2x, like that. And did I forget? Say negative 2. No, that looks right. Okay, making sure I had my 2 there. Yeah, it's right there. This is what happens when you skip steps. Yeah, I know I shouldn't have, but that's okay. Plus, I've got the second times derivative of the first, which is just going to be e to the x sine 2x. Sine 2x. Okay? Now, the derivative of this, which we already have right here. So that's going to be plus and negative 2 e to the x sine 2x plus e to the x cosine 2x. Right? Okay. So now that I've got all of that, I can start combining things. So first thing, let's combine all the e to the x cosine 2x's. So I'm going to have negative 2 times 2, which is going to be a negative 4, and then I'm going to have just a 1 right here. So positive 1, so it's going to wind up being y double prime is equal to negative 3 e to the x cosine 2x. And then the e to the x sine 2x is I've got negative 2 here and negative 2 here, so minus 4 e to the x sine 2x. Alrighty, so I finally have my y double prime, and now I can build this differential equation. So it's going to be y double prime, which is negative 3 e to the x cosine 2x minus 4 e to the x sine 2x. Okay, now minus 2 times y prime, well, y prime is right here, so minus 2 e to the x sine 2x plus e to the x cosine 2x. Okay, and then finally plus 5y, so plus 5 times e to the x cosine 2x. Whew, that was a lot of work. Alrighty, so let's take care of all the e to the x cosine 2x's. So I've got negative 3 here, and then I'm going to have negative 2 here. So negative 3, negative 2 is negative 5, and then I'm going to get plus 5. So all of these go away. Okay, now let's do the e to the x sine 2x. It's negative 4 here, positive 4 here. So this whole big thing equals 0. Check. We have verified that at least this one works It is a solution to this differential equation. Now we're going to have to do this one. And I don't think I'm going to, yeah, I'm going to need to clear at least part of this. So here we go. Magic time. I'm going to try this. Make sure you pause the video if you want to get the details, but I'm about to erase them. So here we go. I'm going to make a giant brush, no, giant eraser rather. And here we go. Erase, 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 erase. Oh, that's so satisfying. Boom, just like that. Alrighty. Now let me reduce the size so I don't get crazy if I have to tap it. Alright, so now let's try the solution. So we have y is equal to e to the x sine 2x. Okay, so y prime is going to be first times derivative of the second, which is going to wind up being 2 e to the x cosine 2x, and then plus second times derivative of the first, e to the x sine 2x. Okay, so that's the y prime. Now I need to find y double prime. So y double prime is going to be 2 times, well, I've got first times derivative of the second, so this is going to be negative 2 e to the x sine 2x plus the second times derivative of the first, which is just e to the x cosine 2x. Okay, so now I can bracket that, and now I have to take the derivative of this, but I've already taken the derivative of that, so I can just add that in. So plus, let's see, I've got all of this, 2 e to the x cosine 2x plus e to the x sine 2x. Okay, so let's handle all the e to the x cosine x's first. So I'm going to have 2 times that plus 2 times that, which is going to give me 4 e to the x cosine 2x. So y double prime is equal to 4 e to the x cosine 2x. And in the sine terms, we're going to have negative 4 here, positive 1 here, which is going to be negative 3 minus 3 e to the x sine 2x. All right. Now let me build the differential equation. So I'm going to start off with y double prime. So I'm going to have 4 e to the x cosine 2x minus 3 e to the x sine 2x, and then minus 2 times what I got for y prime, so this right here, 2 e to the x cosine 2x plus e to the x sine 2x, and then plus 5 times my y, which is just e to the x sine 2x. Okay? Alright, so let's handle all of the e to the x cosine 2x. So I've got 4 here, and I'm going to get minus 4 here, and that's it. So those two go away. And then I'm going to have, for the e to the x sine 2x's, negative 3 minus 2, which is going to be negative 5, plus 5. Yep, all of those go away. So all of this is equal to 0. Hooray! All right. So we have now verified that they are indeed solutions. So the next step is to do the Wronskian. And I'm just going to do what I did before and erase all of this and keep the top. Not needed, but it's just, it looks really cool when I do that. I think it does anyways. It saves me some rewriting, and I need a much bigger brush size. There we go. Erase, 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 erase. Alrighty. So now let's see if they are linearly independent. So I do the Wronskian. So it's going to be the determinant of, I'm going to have e to the x cosine 2x for the first head of the first column, and then e to the x sine 2x for the next column header. And then the derivative of this, and the derivative of this was negative 2 e to the x sine 2x plus e to the x cosine 2x. Okay, so that's the derivative of that, and then the derivative of this is going to, let's say this was positive 2 e to the x cosine 2x plus e to the x sine 2x. Okay? So the determinant of that, well, when I multiply this times this, I'm going to wind up with, let's see, 2 e to the 2x cosine squared 2x. That's that times that term. Now this times this term is going to give me plus e to the 2x times cosine 2x sine 2x. Okay, so that's the first part. Then subtracting this times this. So minus minus, the first term is going to wind up being positive. So plus, I'm going to have 2 e to the 2x. And this is going to be sine squared 2x. Okay, and then this term times this term is going to be minus e to the 2x cosine 2x sine 2x. Alrighty, so let's see, let's simplify this. So this and this cancel, and I'm left with this plus this. So I'm going to get 2 e to the 2x, they both have that in common, times cosine squared 2x plus sine squared 2x. Well, what do you know? Isn't that satisfying? Cosine squared plus sine squared is 1. So this equals 2e to the 2x. So that's my Wronskian. Now, is there any value of x that will ever make this 0? No. This does not equal 0, so they're linearly independent. And so since they are solutions that are linearly independent, I can form the general solution now. So the gen solution, gen sol, is going to be y equals a constant times the first one. So it's just going to be c1 e to the x cosine 2x plus c2 times the second one e to the x sine 2x. Just like that. And there you have it. That is the general solution to that differential equation. That is the fundamental solution. So, alrighty. Now that we have done that, let me clear this and we'll tackle the very last one. So, let's see. Clear this. Okay, the last one is 35. So for 35, we are given that this is for non-homogeneous equation. So we're going to have that the first particular solution, so y sub p1, is equal to 3e to the 2x, and we're told that that is a solution of, let's see, it's y double prime minus 6y prime plus 5y equals 9e to the 2x. Okay, and the way that we verify that is we find what all of this is equal to given this solution, and it had better be equal to 9e to the 2x. So let's check it out. So I'm going to call this just y is equal to 3e to the 2x, and so y prime is just going to be 6e to the 2x, and y double prime is going to be 12e to the 2x. Okay, now when I plug them in, I'm going to get y double prime, so 12e to the 2x minus 6 times this one, which is 6e to the 2x, plus 5 times this one, which is 3e to the 2x. And so let's see, I've got 12 minus 36, so negative 24 plus 15. Oh, that was a negative sign here. Woo, I was going, oh my gosh, I got the sign wrong. No, that is correct. So negative 9e to the 2x. So that one checks out. Okay. We're also told that we have y sub p2, a second particular solution of, let's see, it was x squared plus 3x, and it is a particular solution of y double prime minus 6y prime plus 5y equals, now for the different part, we're going to have 5x squared plus 3x minus 16. Okay? So we'll do the same thing. I'm going to say y is equal to x squared plus 3x. Y prime is equal to 2x plus 3. And y double prime is equal to 2. So let's see if this checks out. I'm going to do y double prime, which is 2 minus 6 times 2x plus 3 plus 5 times x squared plus 3x. Okay? Let's see what that equals. Well, I'm going to get for my, is that right? Yeah, I guess that's right. You know what? I'm going to actually do one more step because I don't want to do that in my head. 12x minus 18 and then plus 5x squared plus 15x. There we go. Now I can combine like terms. So let's see, I'm going to get for my x squared, I'm going to get 5x squared. And for my x's, I get negative 12 plus 15, which is plus 3x. And then 2 minus 18 is negative 16. And what do you know? That works. All right, we have guaranteed that they are solutions. So that was part A, I believe it was. So now we can move on to part B. Alrighty, let's see, how can I do this? I'm going to have to do a little bit of rewriting, but I think I can get away with erasing some of this. Alright, so, yeah, I think I can do this. Alright. That's you know what, I've just erased it. I don't want to, I'll rewrite it. That's just bugging me having to think it's going to be in two places. Alright, you didn't see anything. Okay, and what I will actually rewrite is going to be y sub p2. That was equal to x squared plus 3x. And that one was y double prime minus 6y prime plus 5y equals 5x squared plus 3x minus 16. Alrighty, so here we go. What I'm going to do now is I'm looking at different combinations of these non-homogeneous pieces. Hopefully it'll make sense in just a sec. So let's see. I'm trying to remember where does the book say? I'm looking at it right now. Use part A to find particular solutions of, okay, got it. So it wants us to find the particular solutions of y, this is the first one, y double prime minus 6y prime plus 5y equals, and it is, and if I can copy all this down, 5x squared plus 3x minus 16 minus 9e to the 2x. Okay? So, what particular solution corresponds to this? Well, that particular solution, this part is the particular solution it is this particular solution. So this is x squared plus 3x. And this part is this particular solution up here, which is 3e to the 2x. Okay? So this non-homogeneous part right here is this piece plus this piece. So the particular solution is just going to be this plus this. So x squared plus 3x plus 3e to the 2x. That is the particular solution for this non-homogeneous part. So if I have the differential equation with a non-homogeneous part that looks like this, I can just build that up using the individual particular solutions. So this one is the x squared plus 3x, and this one is the 3e to the 2x. You can always do a linear combination of particular solutions in order to finally figure out what you get when you have a non-homogeneous part that's built out of pieces that you can recognize. Whew, that's a mouthful. Now the second part was, what if I had, let's see, copying this. Oh, yuck. Okay, yeah, it's not too bad. We can figure that out. So it's going to be y double prime minus 6y prime plus 5y equals, so this is negative 10x squared minus 6x plus 32, and then plus e to the 2x. Alrighty? So this piece right here is negative 2 times this piece, right? So this is negative 2 times the particular solution, the second one. And this one right here is negative 1/9 of the first particular solution. So negative 1/9 times y sub p1. Alrighty? So what do I wind up with? Well, that means my y sub p is going to equal, I've got negative 2 times my particular solution, the, where am I? Right here. So negative 2 times, what is it, x squared plus 3x, and then minus 1/9 times e to the 2x, like that. Alrighty, so this was negative 2. How to say this? Gosh, this is so, it's kind of a backwards, twisted way of looking at things. This piece right here matched this piece, but when it was multiplied by negative 2. So the particular solution is going to be negative 2 times the particular solution. So negative 2 times x squared plus 3x. This piece right here is the same as negative 1/9 times this piece. The particular solution for that was 3e to the 2x. Oh, did I forget my 3? I think I forgot my 3. Let me fit that in. 3. There we go. So this is just going to be negative 1/9 times that. So my y sub p for the one that I was given is going to equal negative 2x squared minus 6x, and then minus 1/3 e to the 3x. That's the particular solution that corresponds to this non-homogeneous piece. Okay? So you can always build a particular solution out of a linear combination of particular solutions. and that's totally fine. It's still a particular solution. So check and check. Alrighty, so that was homework. Now let's get back into the fun stuff. We're finally going to have a section. So let's knock out 4.2. So here we go. Let me clear this and let's get started. I can actually clear. Okay, so this is section 4.2 and it's reduction of order. And this is going to be one of the most straightforward methods that we've ever seen. You're going to enjoy this, I hope, because this is a single page of derivation, so it's not bad at all. So let's start off. Bracket that off. Let's say that we have a homogeneous second order DE. So we got a sub 2 of x times y double prime plus a sub 1 of x times y prime plus a naught of x times y. And since it's homogeneous, it's equal to 0. Okay? If we have something that's in this form, we can, using the upcoming technique, we can actually reduce a DE in this form to a first order DE that we can then solve using methods that we already know. And previous methods. You can probably guess which method I'm going to go to. If it is a first order linear, yeah, I'm going for integrating factor. That is just very, very sweet. Alright, so here we go. Bear with me because this is going to sound a little strange at first. Let's say that we have a second order linear homogeneous differential equation. Actually, it would be homogeneous linear second order. But some of those, I guess, qualifiers, I forget the order that they're supposed to be in, but that's okay. So we have homogeneous linear second order differential equation, just like this, okay? Let's say that we know one of the solutions. We are given y1, okay? Now, if y1 and the second solution, y2, are linearly independent, okay? Now, that means, based on what we talked about before, that y1 and y2 aren't, if they're linearly independent, they are not multiples of each other, okay? y1 and y2 are not multiples of each other, okay? So far, so good, okay? So if that's the case, we can say that, here we go, y2 over y1 is equal to some function of x, u of x, but this u of x is not a constant. Why? Why is it not a constant? Well, it's not a constant because they're not multiples of each other, so when I divide them, I don't get a constant. So I get some function u, okay? So if you're good with that, we can move into the actual theory. That's all that you had to believe. Now, keep in mind, we know what y1 is, okay? It's just, and I know that y1 and y2 are linearly independent, y1 and y2 are not multiples of each other, therefore y2 divided by y1 is some u. It's just some function of x that's not constant, okay? So let me clear the screen. Let's talk about that. Now, u of x can be found by substituting y2 equals u of x times y1, okay? Well, that makes sense, right? Because y2 divided by y1 is equal to u, therefore y2 is equal to u times y1. Makes perfect sense, right? Just rearranged it, okay? Now, if I do this substitution, I use this substitution right here, I can find what y2 is, okay? So, I know what y1 is. I know that y1 and y2 are linearly independent. If I do this substitution right here, I'm going to claim I can figure out what y2 was, okay? So let me kind of show you what I'm talking about. This is some of this looks like magic, but I promise it works. So here we go. I'm going to say that I have y double prime minus y. This is the kind of example that will show how to use this. So y double prime minus y equals 0, okay? And we know y is equal to, well, one of them is definitely e to the x, because second derivative of e to the x minus e to the x is definitely 0. So I know that one checks out. So y1 is equal to e to the x. But let's say we have no idea what y2 is. We don't know y2, okay? So what we're going to do is we're going to say y2 is equal to u times y1, okay? So if I use this substitution, I'm going to make one change just so I don't have to write y2 a million times. I'm going to call that y is equal to u times y1, just because I really don't want to write y2 so much, because you'll see I would have to do that many times. So my goal is now to figure out what y is. That's my y2. So I'm going to make, if y is equal to u times y1, okay, then y is equal to u times, well, what was y1? y1 is e to the x, okay? That means that y prime is going to be what? Well, first times derivative of the second. So derivative of e to the x is just e to the x, plus second times derivative of the first, which is going to be u prime times e to the x, like that. Okay? Y double prime is going to be, well, we do the same process. First derivative of the second, plus second times derivative of the first, plus first times derivative of the second. I guess I can put the little dots in there, although they're not really needed. And then plus second times derivative of the first, u double prime e to the x. Okay? All right. So now that I have my y and my y double prime, I can now take that and substitute it into my differential equation y double prime minus y. And I'm already looking at this going, I really wish I had more space. Ugh, I hate clearing this early. Well, I'm going to have to. Just remember, this is my y double prime, this is my y. That's what I'm going to substitute in for this differential equation. So let me clear the screen, and we will take care of that. So y double prime minus y is going to equal, well, y double prime was u e to the x plus 2 u prime e to the x plus u double prime e to the x, right? And then minus y, and y was u e to the x, right? Okay, so, and all that is going to equal 0. Well, I've got a u e to the x and a minus u e to the x, so those are going to cancel. And I'm going to be left with 2 u prime e to the x plus u double prime e to the x equals 0. Okay, I'm going to factor out e to the x, so e to the x times 2 u prime plus u double prime equals 0. Okay, now e to the x can never equal 0, which means that this must be 0, right? Just this piece right here. So I'm going to write that out. So 2 u prime plus u double prime must equal 0. All right. Now I'm going to make a substitution. Well, first off, if y'all are okay, let me rearrange this because I hate having my primes out of order. U double prime plus 2u prime equals 0. Now, I'm going to make the substitution saying that w is equal to u prime. Okay, if that's the case, then this becomes, here we go, w prime, right? So it's just the w is u prime, u double prime would be w prime plus 2w equals 0. Okay, now, does this look familiar? This is the linear first order one that we can now use the integrating factor on, because this is my p of x and this is my f of x, right? So I can now do the whole thing where I do the integral of p of x dx is going to equal the integral of 2 dx, which is going to equal 2x. Mu is going to equal e to the integral of p of x dx, which is going to be e to the 2x. Okay? So, I now have that mu is equal to 2x. So, now I can solve w. Let's see, I'll come back over here. W is equal to, well, it's going to be 1 over my mu, so 1 over e to the 2x times the integral of mu e to the 2x, which I can make a little bit better right here, to the 2x times f of x, 0 dx. Okay? So I wind up with, first thing I'm going to do is multiply, get rid of this thing in front of this integral. So I'm going to multiply both sides by e to the 2x and get e to the 2x. I'm trying to figure out if I can fit all this on here. E to the 2x times w equals the integral of 0 dx. All right, so that comes over here, just so I can follow it. Alrighty, now what did I differentiate to get 0? That means this has to be a constant, right? So I can now say that e to the 2x times w is equal to c1. Okay? So now that I got it in this form, I can say w is equal to c1 times e to the 2x. Alrighty? So now that I've got w is equal to c1 e to the 2x, I can now do a back substitution. Gosh, I need more room. Let's see, I'll box this off. So instead of w, I'm now going to rewrite it as u prime. So I can say u prime is equal to c1 e to the 2x. And now that I've got it in this form, I can take the integral of both sides. Okay? When I do that, I'm going to wind up with the integral of u prime is u, and it's going to equal, well, this is a constant times e to the 2x. I can totally differentiate that. What is that going to give me? What is, wait a second, looking at my notes, where did I mess up? E to the, I've got missing a minus sign. Where's my minus sign at? Hold on. I just made a mistake when I moved something over, I think. Oh, right. Gosh, I'm sure y'all were yelling at the screen when I did this. I was going, holy cow, there's a minus sign that's missing here. It's not going to work. Right here where I have, where am I? I'll go back to here, right here. I have 1 over e to the 2x times this integral is equal to w. So I'll multiply both sides by e to the 2x. So I get e to the 2x times w is equal to that integral. And then I solve for w. But w is not equal to c1 times e to the 2x. It's equal to c1 times e to the negative 2x. Because if I move it back over, I'm dividing both sides by e to the 2x, which is e to the negative 2x. Ooh, gosh, that was making me go crazy. I was like, oh gosh, it didn't work. So here we go. We now integrate u prime. I get u. I'm going to integrate a constant times e to the negative 2x, which is going to be negative 1 half c1 e to the negative 2x x plus some constant when I integrated. Now, y2 was equal to, do you remember? It was equal to u times e to the x. So y2 is equal to u times e to the x. So y2 is going to equal this u, negative 1 half, I'm not going to have room, c1 e to the negative 2x plus c2 times e to the x. So that's my u right here, times e to the x. All right? I want it to clear. Actually, would y'all be okay if I just erased a chunk up here? Because I don't want to do a full clear. I'm just going to erase this. We don't need this stuff right here. It's the problem with these little tiny sections, these virtual blackboards, not enough space. So now I'm going to block this off. And I'm going to say this is where I'm starting, and I'm starting right up here. So y2 is equal to negative 1 half e, I forgot my c1. c1 e to the negative 2x plus c2 times e to the x. Okay, so now I'm going to multiply that through. y2 is going to equal negative 1/2 C1 e to the negative 2x times e to the positive x is e to the just negative x plus C2 e to the x. Okay? Now, this right here is a solution that is a general solution. Let me rephrase that. Can I say that? Is that the right terminology? This is, yeah, I think that's what I said way back, the book said way back when. This is a solution that is generalized. It is a family of solutions that we won't know what the specific particular solution is until we have initial conditions that we can plug in to solve for C1 and C2. Okay? But it should work for any C1 and any C2. It just, I would have to find the specific particular initial condition that would allow me to solve for the C1 and the C2. Now, this is a little bit of a leap of faith, but C1 and C2 are arbitrary. This is the general solution. They are dependent on what my initial conditions are. Therefore, I choose to make my initial conditions such that let C1 equal, well, let's see, how about negative 2 and C2 equal 0. Okay? Now, how did I pick those? Well, you'll see in just a second. If C1 is negative 2, that's negative 1/2 times negative 2. So that goes away and I'm left with e to the negative x. And if C2 is 0, well, that term goes away and I'm left with, drum roll, y2, the second solution, is e to the negative x. If you remember, y1 was e to the positive x, and we were trying to find what y2 could be. We went through this whole procedure, and it turns out y2 is e to the negative x. This is so satisfying. It's like magic. It just popped out of nowhere. We did all that crazy work with the substitutions, and then we had to do everything in, cross things out. We then did a substitution to get in terms of W, where it would be a single, a first order linear that we could then use our integrating factor on. We do all of that. We then go back into U prime, take the integral, get to U, and then we wind up choosing our C1 and C2, and out pops the second solution, just sitting there. So what is this reduction of order doing? If you have one solution, it can tell you what the second one is. So we have one, we do this whole system, and we get the second one. Okay? So I know that was a lot. Let's work through another example. Okay? So let's stop this. Let's go here, clear the screen, and go to another example. Okay, for this next example, let's say, I think this is number 5 in your book if you're following along. We have y double prime minus y equals 0. Well, that looks familiar. But this time we're given that y1, one of the solutions is hyperbolic cosine of x. Okay, and I hope you remember, maybe not, it's been a while, the derivative of hyperbolic cosine is positive hyperbolic sine. And we need an x there, don't we? So this is just, and I'm going to say cosh and sinh just because I don't want to say hyperbolic, hyperbolic, hyperbolic. So cosh and sinh. Okay, so we are, let me erase this. We don't need this up here. Alrighty, so we're given the first solution. Now we need to figure out what the second solution. Any bets? What the y sub 2 is going to be? I'm going to make a bet that y sub 2 is sinh x. But we'll see. Pretend I didn't do that. Here we go. So we're going to start off. We're going to say that y2 is going to equal to some u times y1. So that's going to be u times cosh of x. Okay? So that's my y2, which I said I was just going to call just y, just because it's going to be a lot. I don't want to have to do a whole bunch of y sub 2's. So this is my second solution is equal to some u times my first solution. Alrighty? So that is my, this right here is y equals u times hyperbolic cosine cosh of x. So that means y prime is going to be first times derivative of the second, which is just sinh x plus second times derivative of the first, u prime times cosh x. Okay? So now y double prime, well, it's going to be the derivative of that, which is going to be first times derivative of the second, u times hyperbolic cosine cosh x plus u prime times sinh, and then plus the derivative of this, which is, oh, I'm going to run out of room, first times derivative of the second, so u prime times sinh x, I'm going to have to just do it down here, plus u double prime times cosh x, okay? But when I combine this, this is going to be y double prime is equal to u times hyperbolic cosine cosh x plus 2 u prime times sinh x plus u double prime times cosh x. All right. So that's what I get from my y double prime. Well, now I need to build this up here. So I'm going to wind up with my u times cosh x plus 2u prime times sinh x plus u double prime times cosh x minus y, which y is just this. So minus u times cosh x. Alrighty? And that should equal 0. So those two drop, and I'm left with, and I'm going to rewrite it in descending order of the order. So u double prime times cosh plus 2 u prime times sinh x equals 0. Alrighty? Now, I'm going to make a substitution. Substitution is going to be w equals u prime. So this is going to become w prime times cosh x plus 2w times sinh x equals 0. Alrighty? Now, I'm going to rewrite this in a kind of a different way. This is going to be cosh of x times w prime plus 2 sinh x times w equals 0. Alright, before I can do the integrating factor, I have to get w prime by itself. So I'm going to divide every term by this cosine, this hyperbolic cosine of x. So I'm going to get w prime is equal to, we're going to have 2 hyperbolic sine x divided by hyperbolic cosine x, like so. What do I do? Equals, gosh, that should be a plus sign. W equals 0. All I did was I divide every single term by hyperbolic cosine. Okay, so now I've got this. Well, hyperbolic sine divided by hyperbolic cosine is, yes, hyperbolic tangent. So I don't have a name for hyperbolic tangent. It's not tanth or something weird. So I'm just going to have to say 2 hyperbolic tangent of x, w. Okay, so far so good. Now I can do my integrating factor. So here we go. Integrating factor is going to be, this is my p of x. And what do you know? This is my f of x. So life is way easier than it had to be. So I'm going to get, let's see, there's some scratch work over here. The integral of p of x dx is going to be the integral of 2 hyperbolic tangent of x dx. Okay? So this one is a little bit tricky. You have to actually go back to calculus or look it up online. I do not carry this around in my memory bank, but the integral of hyperbolic tangent is, any guesses? Yeah, of course, it's the natural log of hyperbolic cosine, which everyone remembers, of course, right? So I get the integral of 2 hyperbolic tangent is 2 times the natural log of hyperbolic cosine of x. Okay? Now, mu is equal to e to the integral of p of x dx, right? So it's going to be e to the 2 times the natural log of hyperbolic cosine, of x. Okay? I need the e and the natural log to be touching. I can't have them just separated by this 2. So I'm going to use that log property and pop the 2 as an exponent. So this is equal to e to the natural log of hyperbolic cosine of x quantity squared. Alrighty? And in return, that's equal to e to the natural log of hyperbolic cosine squared of x. Let me write that over here. E to the natural log of hyperbolic cosine squared x. Okay? That's my mu. E, natural log, are going to cancel. So I'm going to be left with mu equal to hyperbolic cosine squared x. This is what my mu is going to be. Okay? So I'm going to clear this and start in on that. Clearing it. So let's see. Let me write that down again. I had mu was equal to, I've got, I'm looking at my paper making sure I didn't want to write anything else first. No, that should be fine. Hyperbolic cosine squared x. Okay? Now, my w, to solve for w, is going to equal 1 over mu, so 1 over hyperbolic cosine of x, times the integral of hyperbolic cosine squared x times f of x, which is 0, right? So I'm now going to move the hyperbolic squared x over and get w times hyperbolic squared x is equal to the integral of 0 of the dx, right? Well, what is, I have to differentiate to get 0, had to be a constant, so w times hyperbolic cosine is equal to c1. So I can now say that w is equal to, I'm going to have 1 over hyperbolic squared x times c1. Okay? Now w is u prime, so I can rewrite this as u prime is equal to, actually, you know what, before I do that, let me do one thing. Let me do a rewrite on this, because 1 over hyperbolic cosine squared is hyperbolic secant squared x times c1. Okay? Because 1 over cosine is secant, so 1 over hyperbolic cosine is secant. So I'll get, I will actually come over here and start that up here, make it a little bit easier to follow. So u prime is going to equal hyperbolic secant squared x times c1. And now take the integral of both sides. And this actually turned out really nicely, because the integral of u prime is u, and the integral of secant squared is, what do I have to differentiate to get secant squared? Tangent, absolutely. So this becomes, if you allow me, I'm going to put it in the front. So c1 hyperbolic tangent of x plus c2. Okay? So now I've got it in this form, and y2 was equal to u times what? You remember? Hyperbolic cosine x. Yep, cosh. So y2 is going to equal this u, c1 hyperbolic tangent x plus c2 times hyperbolic cosine of x. Okay? So y2 is going to equal c1 hyperbolic tangent x times hyperbolic cosine x plus c2 times hyperbolic cosine x. Okay? Tan hyperbolic tan times hyperbolic cosine, well, tan hyperbolic tangent x is hyperbolic sine of x over hyperbolic cosine of x, right? Tan is sine over cosine, so this becomes, I've got sine over cosine times cosine, which just becomes hyperbolic sine. So I have C2 hyperbolic cosine x right here. And now I have got it in a nice manageable form. I'm going to pick two values. So let C1 equal 1 and C2 equal 0. If that is the case, y2 equals hyperbolic sine x, which is what we thought it would be at the very beginning. And it just fell out of all that math. It's a lot. It's a very long, arduous process, but it's worth it, because sometimes you are going to be able, you're either given one of the solutions or you can guess one of the solutions, but you won't know what the second one is. You can then use this technique to lock in what that second solution has to be. So this is a technique that you will see every now and then. So just kind of go through it, learn it, become friends with it, and everything will be just fine. So homework, I'm just going to give you 2 of these because they are quite a bit of work. Homework, and this is from 4.2. Knock out number 1 and number 3. That's going to be plenty of work. I've already worked them out, and I can tell you that's plenty of work. So enjoy this if you go through all the steps and you're very, very careful. At the very end, one of your pieces is going to be what you already knew. That was a solution that you already have. The other piece is your Y2. Okay? So good luck with the homework. If you have any questions, let me know. And I guess that's about it. I will see you later. Stay safe. Bye-bye.